Okay, this is a this is an interesting problem. Okay, so the thing is, you start going north, then you take left turn, then you take left turn, then you take left turn, you continue taking left turns. And you have to tell whether you have crossed the path or not. So, and this two means like you are going, like, 2 units towards north, then one means 1 unit to its left, then one means 1 unit to its left, which means going down basically, and then two means again going 2 units to your right, which means like east direction, let's say. So in this particular case, we are actually crossing ourselves. In the another example, if we go like this, we are not crossing it. Similarly, in this example, even if you touch, actually, it considers that you have crossed it because it went here with 1 unit, 1 unit, 1 unit, and 1 unit. So even if you touch your starting point, you consider that you have crossed the limit. So the problem seems pretty easy to understand what we want to do. Anybody tried this problem?
Yeah, I think that we go counterclockwise, right? And then we go the whole circle counterclockwise.
Mm-hmm.
So my initial idea was like, if we want it to cut, when we go up, up, then the like the value that we go up had to be same or greater than. No, I mean, let's say the value that we going down had to be same or greater than the value that we going up. Similarly, if we go left, and the value that we go right have to be greater than or equal to the value that we go left.
Okay.
So, like for example, in example 2, we see in there. Oh, okay. The value that we go up, and then we go, when we go down, we go greater than the value that we go up, right? So that mean that we're not gonna meet, we're not gonna cross.
But you can continue going that way forever. So how would you? It is just showing you 4 values, but you can have many such values. So how would you deal with that? So you understand this is the final value. Like you won't have 1, 2, 3, 4. This n can go up to, let's see, there is no limit, but the problem has it can have, I don't know, too many.
Oh, is it? I thought only 4.
No. Then it was not hard.
Yeah, that was the same thing I thought upon looking.
And
I
is
thought
also. So
I even thought it's it's not for hard problems because that was pretty easy.
yeah.
Yeah,
My intuition behind this was, if you could see, this is a kind of spiral problem. So there are only 2 ways a spiral can continue without intersecting. Either it is going inwards or it is going outwards.
Awesome.
And there's only, and if it's going outwards, at a single point in time, it can turn inwards. But if it's going inwards, it can never turn outwards.
Awesome.
I think I might have confused a bit people, but
No,
if you just...
I will explain that. I will explain that concept. Thanks for bringing that up because it was not my idea. I did read about it. I did draw some diagrams to prove myself, and then
it's
I will try.
as easy as it to explain inward and outward. The implementation and the corner scenarios of this are very hard.
Yes. So anyone else tried other ideas? Because I did also thought about this, like, after going through the solution, and we will discuss that anyway. But anyone else thought about any other ideas or tried this problem? Okay, probably not. So let's try. First of all, the brute force way of doing this after, because this is a good solution, so let's talk about it later. Like, what you could do is, these are all xy coordinates. You have many xy coordinates. So from two xy coordinates, you can say that I know a line, right? A line is basically x1, y1, x2, y2, and then you know entire details about that line. And these are horizontal and vertical lines. So we can figure out whether two lines are intersecting or not based on their value of x and y directly, right? Because your line could be like this. Suppose this is a vertical line. If this is a horizontal line, I know it will not intersect if I just check these x and y coordinates, right? Because it will lie inside this. Or if it is a like vertical line like this and there is a horizontal line, I know that this will not intersect, something like that. So assume, and this is a smaller problem to solve. So assume you have this thing, a tool to figure out whether two lines are intersecting each other or not. How to solve this problem? Is that fine? Like, we will go to the like next part of the solution.
Hello.
Go ahead.
Can you explain again?
So two lines, if they are horizontal, they will never cross each
Yeah,
other. That is fine because they will
yeah,
be
yeah,
parallel. But if
yeah,
two lines are like not parallel, so one perpendicular and another is horizontal, then how can we determine whether a line crosses the other line or not?
yeah, yeah,
You can check these coordinates and these coordinates to derive that, right?
yeah, yeah.
So it's like, after spending a couple of minutes, you will figure out how to do that. It's not the main
Yeah.
problem here. So suppose you have this figured out. Now what you can do, the brute force way is, since you have been given all this point, like, here to here to here to here to here, like something like this, you can continue putting this line into some storage, let's call it Q or something. And every time you add one line, we'll check whether it is crossing with the existing lines or not. So if I have to draw a more like, thing, when I'm drawing this line, I will check, hey, I will not worry about this line because I know I originated from this line. So it's not a problem. For when I'm adding this particular line, this line, I will check with, I will not check with like, horizontal line, because horizontal line is perpendicular. I will check with this particular line. I will check with this particular line, and I will check with this particular line, right? Because I'm keeping the coordinates, and I will keep doing that till I see if nobody has crossed this. We know that they didn't cross each other. That's a basic brute force approach. Like, we are trying to simulate what was told without adding any intelligence to the like problem.
Why why wouldn't we want to check the horizontal line? Because they could both on the same horizontal line, right?
Oh, you are saying why? Okay, you are saying if we were here and we
Yeah,
go like this.
right.
So you are anyway checking with this guy, right? So it's,
Oh, okay, we already,
yeah, we are checking with
okay,
vertical,
got
so
it.
he will catch it.
Yeah.
So this way you have one solution. If you draw multiple examples, you will figure out, because while you are making it larger and larger, like this, or smaller, you only care about last couple of the checks. Because see, now this guy, there is no need to check this guy if I am already checking this particular line, because it will totally have this smaller line inside it. Make sense? Like when I am adding this line, if I just add check with this line, or even actually with this line, there's not much, after a certain depth, you can start to prune your, hey, don't even worry about after a depth of 5 or after a depth of 4, whatever. So you will not have all the points inside your queue. So your queue size is not growing exponentially or linearly even. Like you don't have to care about every time going to all the n values inside your queues. Don't go inside that. Just check last couple of 4, 5, and you're good. So your queue size then can be reduced anytime your queue size grows more than 5. Just drop these values. Sounds good? This is the brute force approach we are talking about with some optimization. We just added this optimization. And I will share the solution. It's on Discuss, so I don't have to write code, but after going through this, maybe that will make you more sense. So you can just go and read the solution, verify if you want, but conceptually, is there a problem?
Why do we need to check it with the previous 4 5? Actually, we could do it with the last parallel edge. No, sorry, the last to last perpendicular edge, I guess.
So you are seeing only the happy path. Your stuff could be like,
Oh yeah, okay, got
right?
it. But there could be multiple cases for that as well. Then we can't restrict to 5 even. No. Yeah, I got it. I got it.
You
We'll
got the
go.
idea. Like here now
Yeah,
you have a different new rules.
yeah,
You are in a different zone. So you will have to spend some time to make sure that, hey, actually those don't make sense. Don't check that, but that is an optimization. You can always go and select all the points
yeah,
if time complexity allows it. So that is the brute force way to simulate this algorithm, right?
yeah.
Now, if we are done, we can go to the actual good approach, or um, to learn from the pattern and then try to solve this problem.
Yep.
Yeah.
Great. So let's clear this. Okay. Give me 1 minute break, and then you guys can talk during that time if you have any questions, and then I will be back in 1 minute, guys.
So I just want to ask one question. So we only have 4 directions to move, or we can move like any directions. Like we have n number of.
Yeah, we can move in n number of directions. Actually, the examples show just 4, but you could make any sort of path, If there are multiple even after 4, then we'll go on, we'll keep on going in the counterclockwise direction with the units whichever it will be given.
Yeah. Direction will be 4, but the input can be a stream. So
Yeah.
any number of input integers will be keep coming, and you need to move based on the previous direction you moved.
Yeah, so we will be moving in 4 directions. Always we are going left from north. We start with north and keep going left. So there are 4 directions, and you can have any number of steps So it's not just 4 steps. So any question on that? Was it Sonia?
Yeah, it's me. It was me.
Okay. So do you have any further questions before we start the other approach?
In the at the beginning, you mentioned there's a inward and outward. Can you elaborate on it?
Yeah, we are going with that approach now. So let's do that.
Okay.
Why not we go with that approach? So, happy case, like, you start like this. You start like this. So what you are doing is going outwards. That's what we are calling that. Hey, if I keep going, like, increasing my value 1, 2, 3, 4, 5, then I will never be in a problem, right? Because it's growing.
Yeah.
So, right? So
Yeah.
this is one happy case. If you go like that, and if your input is like that, then like it's a sorted input, suppose 1, 2, 3, 4, 5, 6, 7, 8, then you can say, hey, no problem. I will have no problem. I can just visit all the places. I'm not self-crossing. So how would you determine? It's like you will say that, okay, when do I know that I am not self-crossing is keep going outward. So if you check that wherever you are, like here, 3 and 1, let's look at it. So 3 is bigger than 1. So it determines that you are going outward, right? Because if 3 was less than 1, then because you know that you will take a right turn from wherever you stop. So if I take a right turn here, I will cross this line eventually, or I may be trapped basically. But if I go further than this value 1, then most likely I am going outward. Actually, I am going outward. So all you are looking at, if I am at 4, I am looking at where was my horizontal last direction. So from 4, I can look at 2. If I'm going behind 2, then I'm going outward, right? So you keep going that. I think this is the implementation detail, but this is how you determine that you can go outward. Happy case 1. Next happy case, as someone was talking about, is when you go inward. So going inward means like opposite direction. You started like this, you started going like this. Still, we are not self-crossing, right? Because we are going in this particular direction. Everything is fine. Till suppose this was my last point, I can say this is also a happy path. However, there is a difference between being happy in this first way and the second way. Can someone tell me what is that? We talked about it already. So the guy who suggested, he talked about it.
I think in the inward case, whenever we'll go outward, it will, it will be a self-crossing path.
Yeah. It's a good observation that when we are going inward, we are restricting ourselves, that now we cannot go outward no matter what we do, because we have made this circle towards ourselves. Where can you go from now? The only way to continue is you can continue growing inward, right?
Yeah.
But this guy, he can see what he can do. Like, this guy, he's growing outward, and suppose he decided to go inward, he can actually start a new cycle here. Something
Yeah.
like this he can do, right?
Would that be the same for the other case? Because you go inward, then you go outward, but you're not crossing, right?
From inward, how would you go outward? Because here, how would you go? Like, what will you do here? Like in this point?
No. Yeah. No, I mean, you can go outward, but you're not touching the other edge, and you go.
Oh, if you are not touching other end, then you are still going inward. Think
But you
about
go
it.
on opposite direction.
We can't go in opposite direction. Actually, we have been given with that data
Oh,
that
okay, okay,
counterclockwise
okay,
direction all the time.
Does that make sense?
yeah.
So, so the difference between these two happy cases is this observation that if I am coming from outward to inward, it is still a good state. But once I go inside an inward trail, I cannot go outward. I have to continue going inward. So, okay, so that is one observation. Now, what can we do? Like, one place where you can start doing this is you can also go inward like this, right? I mean, just to make sure that it's not just this particular case. You can also start going inward like in this particular case. And whenever you go inward, um, there are certain cases you have to look at. So first of all, how would you determine that you are in an inward way, that you compare your previous to previous, like, direction, that am I trapped or not? You can go to the code to determine that. It's easy. But here, after you are in inward trail, now your boundary is not the same. See, your boundary is now, you are setting a new boundary for your trail basically. This is the maximum now you can travel in because you are in that trap already. When we were going outward, we were just caring about, hey, what was my previous same direction distance? If I'm going, if I'm like, going with even 1 unit more than that, I'm in outward trail. So once you determine that you are not in that trail, you have to check your boundaries. Okay, what is my new boundary? If I update my new boundary, then we are again after updating the boundaries. So you update your boundary after detection. It may not be required. It may be required. We can talk about that case also, maybe. You are going to this happy case. So these two happy cases are pretty trivial to implement, as we can, like, we will post the question solution. And detecting this boundary is the crucial part of it, like how you detect that. Once you detect that, that okay, I'm out of this loop and I'm going into inward, let's reset boundary, and then just do these 3 steps. So your step is check whether you are going outward, first of all, outward. Then if not, because as long as I'm going outward, everything is fine, that's the best case, and it has more leverage that I can go inward but not the other way. Do I need to check my boundary? Check boundary, because now I'm not in my outward. So check boundary. After you check your boundary, then you start inward trail. So these 3 steps are there. Anyone has any questions or want to elaborate anything?
I thought like we check boundary when we go inward, right?
We check the boundaries in both cases, whether we go outward or inward, because how would you know that you are going outward? Without checking the boundary,
Okay, yeah.
you cannot determine that.
Mm.
But when that transition happens, then you now see, now this area is a different rule. This is not the same rule which these guys were having when they were going outward. Now his boundary is like limited to this particular area, right?
Right.
So that's why you do that check, and that guy's solution I can show you, and then let's, like, If you have more questions, we can just.
So that would be linear runtime.
Yeah. So exactly, this is what that guy was doing. It's a, I have also put the reference of this code. This is the code I was looking at.
Posted
So,
my solution also on the Slack.
oh, nice. So same thing, we are keep going outward. We keep going inward here, and in between, we check whether we need to change the new boundary or not. And for that, you will do these checks. If you draw the picture, it will become evident what we mean. But if anyone has any problem, I can go and try to explain that too.
This is updating the input array
Yeah,
also, right?
yeah, it is updating the input array because here he
Okay.
just changed his boundary
Yeah.
here. This is the core point that
Okay.
he changed his next boundary, and that's it.
Okay. Okay.
Yeah, it was in a math category, I guess. Related topics tells me math. So yeah, it was not any like algorithm data structure problem, but yeah, like it's interesting problem. Anyone has any questions or suggestions or anything? Or need more explanation?
No, I think we're good.
Okay.
I'm not sure how is this transition part working on.
Okay. So we can discuss it now if you have time, or I don't know, we are over the limit of
No, I can take a look. I can take a look at the link. If you could just post the discuss link on the Slack.
yeah, if you debug, you can do that. But I have already done some research, so you can ask me maybe for particular example. I can give you that, so you can debug better.
We can stop recording and you can explain about it if we run out of time.
Sure. We can do that. So we are done with the